All right. So, hello and welcome everyone to week 7 of interactive live sessions for the course on fundamentals of convective heat transfer, which is being taught by Professor Amaresh Dalal from IIT Guwahati. My name is Debjit. I'm a TA for this course, and like every week, we shall be solving some practice problems. So, with that, let us begin. Move on to question number 1 of this session. So question 1 says Grade's number G is defined as what? There are four options. After you have read the options correct, pick the correct one. So is it option A, G equal
Answer
to
B. Answer B.
answer D or B?
B. B. B.
B for Bombay?
Huh.
Okay. Uh, okay, anyone else would like to answer?
Same, sir. B.
Option
Bombay.
B. Okay, so very quick responses and correct responses. So this is how Grade's number is defined. So it's Reynolds number by Prandtl number, Reynolds number into Prandtl number divided by x by d. This way, so we can say that G is nothing but Reynolds number, Prandtl number into d divided by x. And remember, this quantity, this actually scales as the entrance length. So Grade's number, you can say that is a way of expressing how many entrance lengths have we covered by x. So 1 by g, in fact, is used as a non-dimensional scaling of x, where this non-dimensional parameter x star is nothing but this x by re Reynolds number into Prandtl number into some characteristic dimension. So what this tells us how many entrance length has have we covered if we have moved from 0 to x. So keep this in mind. This might prove useful in one of the later problems that we are going to face today. Okay, moving on. Moving on to question number 2. Brinkman number, another non-dimensional number which was discussed in the lectures last week. How is Brinkman number defined? Is it so? There are also four options given here. Try to pick out the correct one.
Option A.
A.
Option A.
Option A.
Okay. Again, very quick responses and correct responses. So, Brinkman number is defined as mu into u square by k into delta t. So, as we have, we can quickly recall that Brinkman number is nothing but the product of Prandtl number and Eckert number. Prandtl number we can write down as alpha by nu or nu by alpha.
Nu by alpha.
Nu by alpha. And Eckert number is nothing but u square by Cp into
Delta T.
I think it is rho Cp, is it? Or no? Let's see, dimensionally, this is meter square per second square. And
Now, if you are putting mu Cp by K, then it will come directly.
okay, so let's.
Nu is nu by rho.
So this is nu by rho Cp. Sorry.
Mu Cp by K. No, no. If you are putting like this, nu is mu by rho and alpha is K by rho Cp.
Correct. So is this okay?
Yes, yes. This is okay.
This is okay, right? So Cp into delta T. Cp gets cancelled out and we arrive at the form given in option A. So mu into u square divided by k into delta T. Okay. So moving on, the fully developed temperature profile in a plain Kuwait flow is always linear in nature. Is this statement
True.
true or is it false?
True, true.
Okay. Any other option? Any other answer?
No, it may be.
No, 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 no.
Not be
It
always
is
linear. If viscous dissipation is considered, then it may not be linear, I think.
Not be linear. Correct. So that is why this answer is this statement given here is false. So
yes, yes,
if I
yes.
have Kuwait flow where this is moving with some mu naught and this wall is stationary, Uh, the velocity profile is linear, of course, but let's say the temperature profile does not have to be linear. It is linear only if there is no dissipation. If there is some dissipation, it could be something like this, or uh, it could be a curve with a maxima anywhere.
Means that Prandtl number and Eckert number product is less than 2, equal to 2, and greater than 2.
Correct. So that would determine the slope over here. That also we will look later on. Other than that, if there is any dissipation at all, then it won't be linear. And if dissipation is not considered, then it would be perfectly linear. And whether to consider dissipation or not depends on the value of Eckert number or Brinkman number. Any of them would guide us towards whether to consider viscous dissipation or not while writing down the energy equation. Okay. So once again, moving on to question number 4. Question number 4 says, consider the following statements about Brinkman number. Statement 1 is, if Brinkman number is much greater than 0, temperature rise due to dissipation is significant. And statement 2 says, the Brinkman number is important in case where a large velocity change occurs over short distances. So
C. Option C.
option C, both 1 and 2.
Both are correct. Both are correct.
Both are correct. We are moving really fast today and correctly as well, which is more important. So once again, if Brinkman number is much greater than 0, this signifies that the Brinkman number. How did we write that down? So uh, this into u square. Sorry, mu into u square divided by k delta t. So Brinkman number being much greater than 0 means this numerator is pretty high. So simply we can think of where the velocity is pretty high, and velocities being pretty high is usually associated with the gradients being pretty high as well, and that results in a significant viscous dissipation. And similarly, the Brinkman number is important in a case where large velocity change occurs over short distances. So this statement is also conveying a similar argument that large velocity change over short distance means the gradient is high. So this being high means the dou to u dou I to could also be high, and this is actually proportional to the viscous dissipation. Okay. So which is why both these statements are correct, and option C would be the correct selection. So very quickly moving on to question number 5 of today's session. So consider the following statements. So statement 1 says Grade's number represents the ratio of the time taken by heat to diffuse radially into the fluid by conduction to the time taken for fluid to reach given axial distance. And statement 2 says that for small values of Grade's number, radial temperature profiles are fully developed, but for larger values, the thermal boundary layer development has to be taken into account. So read these statements carefully and pick out which ones are correct, and then select the correct combination from the options given below. The options are option A, only one is correct. Option B, only two is correct. Option C, both are correct. And option D, both are incorrect.
Which- Sir, one is correct definitely. Radial temperature profiles.
Take your time. There is no rush. Like it's been only 15 minutes. and we're already pretty far down now. So
Only one is correct, I think.
okay, so only one is correct is one response. So I'll try to break down these long sentences a bit. So the first one says Grade's number represents the ratio of time taken by heat to diffuse radially into the fluid by uh, by conduction. So let's leave that out. To the time taken for the fluid to reach given axial distance. And the second statement says for small values of Grade's number. So we have to consider, Grade's number much less than one kind of a thing. Or conversely, we can think of where the inverse of Grade's number is much greater than one. Radial temperature profiles are fully developed. So mostly we have been looking at the radial temperature profiles only, and the axial changes only occur in the development zones. So here it says that for small values of Grade's number, the radial temperature profiles are fully developed, but for larger values, thermal boundary layer development has to be taken into account. So the if I simplify this statement down, depending on the Grade's number, whether we can predict that the flow that is being considered is fully developed or not. Simply, this is the thing that from
I,
Grade's number, whether we
I
can
think, sir,
predict.
both are correct.
I think both are correct. So we'll have a look at the answer, and indeed both are correct. So
As what my understanding is,
yeah.
actually, I have seen one graph in the lecture.
Hmm.
That graph is Nusselt number against one by great number,
Correct. So it was
and the
like this.
graph go on decreasing and becomes asymptotic, but
Hmm.
constant.
Yeah.
So
So
fully
it's
developed flow takes
something.
place on right hand side, and initially it is entrance zone.
So the curves were something like this, right?
Yes. Nusselt number is higher at the start
Yeah.
in thermally developing flow.
Hmm. So this was for the constant heat flux case. Sorry, not zero, but some constant. Sorry. And this was the one for constant wall temperature. So these values we know they converge to 4.36 and 3.66, right? So
Yes.
this is the same for fully developed, like both hydrodynamically and thermally fully developed flow. These are the values. So uh, we discussed earlier that this Grade's number or inverse of Grade's number, this is one way of writing down a non-dimensional x, and this is equal to some x divided by d re into Prandtl number. And as this x goes on increasing, which means another thing also I said that this denominator d into re into Prandtl number, this scales as the entrance length. So we can say that if x is high, that means multiple entrance length has already been covered. So that means what? In one entrance length only, the flow becomes fully developed. That's how we define entrance length. So this being high or this G inverse being high means that the flow is getting more and more fully developed. So that's why these values of Nusselt numbers, they approach a constant value asymptotically, and that constant value is that of both hydrodynamically and thermally fully developed flow. So that's the basic concept here. And if we come back to the individual statements, so statement one says that Grade's number represents the ratio of time taken. So that's also one way how we can define Grade's number. So we will write this down once again. So Reynolds number, Prandtl number divided by x by d. So Reynolds number we can write down as mu into some u. Sorry, what am I doing? U into some length scale divided by uh, nu, and Prandtl number we can write down as nu by alpha, and we have x by d over here. So upon a bit of rearranging, we can write down this as d square by alpha in the numerator and x by u in the denominator. So if we look at the numerator alone, so d square by alpha, that is one way of saying that how much time does it take for heat to diffuse uh, you know uh, radially outward. So this d could be the diameter, so d square by alpha which is the thermal diffusivity. So this is actually a time taken for heat conduction to occur radially, so we can call this t1. So this was this time taken by heat to diffuse radially into the fluid by conduction alone. And this one, x by u, this also has units of time. So this is simply distance by speed, which gives us time. And this time t2 is nothing but the time taken for the fluid to reach a given axial distance. So if the axial distance is x, then how long does it take for one fluid particle to cover the distance x? That is nothing but x by u, where u is the velocity of the fluid, and that gives us the second time t2. So Grade's number can be thought of this ratio of two different times. One is time taken for conduction, radial conduction, and the other one is time taken for axial transport of the fluid. So this is why statement 1 is correct. Now moving on to statement 2, for small values of Grade's number, radial temperature profiles are fully developed. So small value of Grade's number means inverse of Grade's number being high, meaning this x star being high. So that means it would approach fully developed. But for larger values, which means Grade's number being higher means this inverse of Grade's number being smaller, and that means we have to consider a developing thermal boundary layer. So that's how from Grade's number alone we can decide whether to consider fully developed flow or developing flow. Right?
Yes.
No. So moving on to question number 6. Question number 6 says, consider the following statements. Okay, this would be statement. There is a typo here. So this would be statements regarding heat transfer in plane fluid flow with upper and bottom plate maintained at different temperatures. Here also temperatures. Okay, too many typos here. At different temperatures, where the upper plate temperature is higher than the bottom plate. And we have three statements, including Eckert number into Prandtl number. We know that this is nothing but Brinkmann number, so we can think of it both ways. So first statement says, when this Brinkmann number is less than 2, heat generation within the fluid is small, and therefore heat still comes in from the hotter top wall. Statement 2 says, if Brinkmann number is greater than 2, the heat generation is so large that heat has to be removed from both the walls, both the top wall and the bottom wall. And statement 3 says, when Eckert number into Prandtl number or Brinkmann number is exactly equal to 2, there is no heat transfer on the top wall, which is the hotter one.
Answer D.
Answer D, 1, 2, 3, correct. Okay. Any other answer? Okay, so if we look at the solution, D is in fact the correct answer. So I'll try to draw a figure and have a discussion on this. So here we have a hotter top wall at say TH and bottom wall at say T naught, which and TH we know is greater than TO. Now this we can consider TH and this we can consider TO. So so when there is no heat dissipation as we discussed earlier, this temperature profile would be perfectly linear, and the gradient would be the same everywhere. We have seen that in the case where Brinkman number is exactly equal to the Nusselt number becomes 0 at the top one. So I'll try to take a ink of a different. So there, this gradient is 0. So there will be a perpendicular line to the wall over here. We try to draw the temperature profile, and then later on there would be a curve like this. So this is for exactly equal to, and if the Brinkman number is greater than 2, then we know that Brinkman number being high means dissipation is very high. So that means the fluid itself gets, due to dissipation, gets much hotter than both the walls. So both TH and T0 are lesser than the maximum temperature which occurs within the fluid. So heat gets transferred from the fluid to both the walls. So the temperature profile would look something like this, with the maxima in between. This is for greater than 2. And on a separate case, I'll try to draw this with green. So on a separate case, if Brinkman number is less than 2, then also there is some dissipation. There is heat generation within the fluid, but it's not so much that it gets higher than the hotter wall or TH. So in that case, there would still be a heat transfer from the wall into the fluid, but however, the temperature profile no longer remains linear. So that adds a curvature to it. So there will be a heat transfer from here, but there will be a curved line coming in here. So this blue one I'm trying to draw here, this blue one is for less than 2. These are all values of the Brinkman numbers. So the Nusselt number at the top wall, this is 2 minus Brinkman number, and the Nusselt number at the bottom wall, this is minus of 2 plus. Okay. So the value of Brinkman number being 2 means what? So we'll look at separate cases. So if the value of Brinkman number is 2, then this Nusselt number at the upper wall, this becomes 0. So this corresponds to the case drawn in the blue line where the gradient becomes 0, and the bottom wall is minus 4. One thing to consider here, we never saw negative signs before Nusselt number earlier. So this simply means that the heat is transferred from the fluid into the wall. We always considered Q to be positive if heat is transferred from the wall to the fluid. Sorry, so negative value means the heat is being transferred in a different way, in the opposite sense. If it's less than 2, then that means this would be a positive value, but greater than 0. So Nusselt number here would be greater than 0. And this Nusselt number at the bottom wall, this simply is some negative value which is somewhere between 0 and sorry, not 0, 2 and 4. Sorry, minus 2 and minus 4. So this would lie somewhere between -4 and -2. And in the last case where there is a significant dissipation where the Brinkman number becomes greater than 2, so these are all Brinkman numbers. So if it becomes greater than 2, then this value becomes negative. So this becomes less than 0, which means heat gets transferred to the hot wall as well. And here also any limits can't be put, so it would be less than -4. Could go from -4 to infinity. That depends on how much dissipation is going on. So does this make things clear?
Yeah.
Okay. So that was all for today's session. So any questions from your side?
Sir, one question is there which is related with assignment. Do you have that copy? Means assignment means previous assignment for which solution has already released.
Previous assignment. Okay, I'll try to pull it up. Give me a second. Yeah. Is my screen visible? So this is week 6, assignment 6.
Yes.
Okay. So which question?
Just scroll down.
Sorry.
Percentage rise something.
This question 6.
Yes.
So the increase in heat transfer in case of uniform wall heat flux boundary condition compared to uniform wall temperature condition is what percentage? Okay. So uniform heat flux. Okay. So here it's not mentioned whether it's a flat plate or a
Means it's whether it is a Cauchy flow or means through flat plate channel or maybe a circular tube.
It could be both. That is not mentioned, right?
That is not mentioned because the answers are different for both things.
Answers will be different for both. Okay, I think we discussed this the last day also, no?
Even on okay, we'll take actually they have taken while calculating that 16 answer na they have taken a reference of circular pipe.
Circular pipe. But this as a question is not correct. So the proper information should be given.
Yes, and another thing, we have solved it by assumption of circular tube. In that also means I have seen the solution because they have given solutions also.
Okay.
In that solution, what have they have done? For uniform heat
solution over here. I'll open up their solution as well. Yeah, this was the one. Is it properly visible?
Yes, it's visible. Now you see it is 4.36 and 3.66.
So these are the values for circular pipe.
Now we have to calculate. I think we have discussed this thing and same question they same thing they have done. Now it is a percent increase we are calculating.
So it should be with respect to the smaller one.
Yes, and it has to be 19%. And this question you have taken in practical session also, sir. We have discussed that thing.
Correct.
And they have given us 16, so we lost one another question there, 10 marks.
Correct. So you raised this concern. I'm not sure how I can help you, but yes, I agree with you fully that it's wrong on these two fronts. So one is the language in which the question was written, and two is the data itself was insufficient.
Yes. Similar kind of questions are there in assignment number 7 also that we have to submit on tomorrow. but the questions, similar kind of questions are there where such ambiguity is there, and two questions are there. Here also you can go down, sir.
Yeah, I'm trying to open it up. This is the previous one only. Yeah. So assignment 7. Numerical type question. There was one numerical type question.
No. Numerical is okay, no problem. That we have solved. You can come to top. No, not it.
2 and 3.
For uniform surface heat flux, the value of Nusselt number for hydrodynamically developed and thermally developing flow in a circular duct is. Now, see, our guess means what logic says. Uniform surface heat flux condition for fully developed, that is hydrodynamically and fully developed, thermally fully developed, the answer is 4.36.
Correct.
Okay. Now it is a developing flow, hydrodynamically developed but thermally developing. That means Nusselt number should be higher than 4.36. That is my logic.
Yeah.
Now here my answer is 4.46. But why 4.46? That can be anything.
Anything. It could be 500, 10,000, anything.
So here I can write as 4.46 is my answer, whatever I have finalized.
So the thing is, you have to make a guess from the options given.
But see, sir, if we are going by that logic, if you read the third question, then the problem comes.
Okay,
see
so
here.
there could be multiple options. Which
Yes. Second option is okay. We can guess it should be greater than 4.36.
Okay, so third.
But if you are getting third for uniform
wall temperature condition, similar thing is given, and then 4 options are here. So here our guideline is it should be greater than 3.66.
Yes.
As I can see, there are two options.
Two options. Now which one we should select? Logic says it has to be greater than 3.66.
These are not expected. Like very gross errors are creeping into these assignments. I'll try to convey this, but please understand that these are not in my hand.
Yes. Actually, it has happened in more or less in every assignment, sir. Some data is missing or something is happening in calculations or like that. That is the problem. Even after sending the message to you and through mail only, then they have uploaded the answers. Before that, there were no answers also, solutions.
Oh, okay. The solution uploading was also not there.
Yes. Now come to the question number 4, sir. There is also a problem.
The shape of the fully developed temperature profile is same as temperature profile of thermally developing flow.
As per my knowledge, means what we learn from you and sir, this temperature profile shape is not same. There is always a difference. Some developing and develop.
Yeah.
That difference is there, and that is negative.
Yeah, correct.
What we learn from the lectures. Okay. So first answer is wrong.
Okay.
First. Then for the similar condition, the values of convective heat transfer coefficient are more in forced convection than in free convection. It is but obvious correct. Means 2 is correct. In the thermally and hydrodynamically fully developed, दोनों fully developed है, with constant properties in a circular duct, the wall heat flux increases exponentially with x. Probably this is also true.
Wall heat flux increases exponentially with x. This is for week 7, right? I'm not sure I'm allowed to, discuss.
Okay. Don't say answer, but see here the problem is what? The answer number 1 is correct. Third discuss करने की जरूरत नहीं, but 1 and 2 are correct.
No, 1 was not correct, right?
No, not correct. Sorry, there is a difference.
Yeah.
So 1 is not correct. Second is पक्का correct है. Second.
Yeah.
अभी थर्ड का है, बट अब सेकंड थर्ड करेक्ट भी हुआ तो सेकंड थर्ड करेक्ट का ऑप्शन ही नहीं है उसमें.
कॉम्बिनेशन विद सैटिस्फैक्टरी.
चलो थर्ड रॉन्ग भी हुआ तो सेकंड करेक्ट का ऑप्शन भी नहीं है उसमें. तो ये भी क्वेश्चन प्रॉब्लम करेगा. यस. So such kind of issues are there. And
thinking about the first statement, so shape of the fully developed temperature profile is same as the temperature profile of the thermally developing flow.
डेवलपिंग में वो लैक करेगा ना प्रोफाइल सर.
In developing flow, in between, like in the undeveloped zone, you can say the core zone, uh, there the temperature is same as Ti, that of the incoming fluid, and
Correct.
in the within the boundary layers there will be a temperature profile. But uh, yeah, I think it is correct. The within the boundary layer, those shapes are same, no, for both, because both of them have the same governing equation.
But whether they have mentioned that within the boundary layer,
That is
they have
the
not
question.
mentioned that.
They have-
That's the issue, no?
So questions are leaving many things up to assumption. So that shouldn't be the case.
Mhm. That's the problem.
I will, I'll try to talk to sir directly about this.
Yes, yes,
Let's see if
that's
we
good
can.
for us. I think probably these things are done by some assistant of
Some,
sir, probably.
someone like me only might be handling it somewhere. So
Mhm.
basically, teaching assistants are taken for these. So
So
anyway, I will try to do what
yes,
I can. There is not
yes,
much
yes.
power in my hand, but I'll try to.
No, no, no. At least you are informing, na? They may be serious on
And
this issue.
last week also, I told them that uh, a few issues you had, right? I forgot what happened later, but then I did.
No, no, no. Same thing. They have asked me to see the solutions, and they have uploaded solutions, but solutions are wrong, na? That's the problem.
Okay, I'll talk to sir about this. Let's see what he says. I'll let you know.
Yes, yes. And one another thing, sir. Mostly we are discussing the conceptual questions. That is a theoretical question, but
Yeah.
there is a conceptual
Hmm.
things. We are not discussing the numericals now. Actually, we are having some doubts in mind. Ki in the final examination, most of the things are coming conceptual because numericals are not. Even sir is also not covering numerical. That is only everything fundamental.
Yeah, right. So nature of the course is kind of like this only. I'll say this unofficially. I don't think very intense numericals can't be expected. Just making use of some final results which were drawn by those very intensive derivations. Uh, those final results has to be put into use.
Yes, yes, yes. Because sir is also not covering, and you are also touching to the fundamentals
Yeah,
mostly. Yes.
I'll try to do that only. Like
Mhm.
because
Yes, sir.
most of the lectures, if you think about, more than 90% is just derivation only.
Yes,
So,
yes, yes.
and most of it is mathematics intensive. So I think somewhere, if I can contribute to more of a physical understanding, then uh, that could be beneficial. So that's what I try to stick to, and that has been my strategy from the start.
Yes, yes. But probably is what my thinking is ki, the question in the exam is are like this conceptual only, means fundamentals.
Yeah, that also I know. I don't
And
know
yes,
what sort of
yes.
questions will come, but
Mm-hmm.
anyway, very difficult things I don't think will come. I'm telling this unofficial, like off the record.
Mm-hmm. Mm-hmm. No, but definitely they are not going to ask to derive that long,
No,
long derivations and all these
derivation
things.
mode.
Yes, yes.
That's very unlikely.
Yes, sir. Just do that help.
Hmm. Okay.
Send the message to sir. That
Okay.
will be great help to us.
Okay.
And I received the book by Dalal, sir.
Correct. I sent it to you.
Yes, yes. And thanks for it.
Okay. Thank
Thank
you.
you.
It has been great. We will meet again next week.